Okay, hello everyone. Welcome to the category theory track. I'm pleased that Richard Southwell is here. So Richard has a YouTube channel where he makes ideas about mathematical topics, including category theory, popular. We're really happy to have you here, Richard. It's great that you took your time out to come here. Richard is a mathematician. He does know something about things about Haskell and programming, but he said I said that it would be really nice to take a look at this topic from a mathematical perspective instead of jumping in from the programming perspective, and I thought that it would be really nice to have him. And Richard has a YouTube channel. I already mentioned that. Yeah, cool. Thank you very much, Richard, for agreeing to be here.
Thank you, Fahad. Yeah. Hello, everybody. It's really cool to be here. I'm used to making YouTube videos in my room at home, and now I have to talk in person, so it's a bit different. I'll have to get used to it. I'll have to suppress the urge to advertise NordVPN. I've sort of not suppressed the urge for clickbait, however. This is the title. What I'm going to do is, for the first hour or so, I kind of want to say basically what category theory is about and what's so great about it, kind of talk about the big three, the Holy Trinity, as it were, the categories, functors, and natural transformations. So I guess it's Pentecost, so if I get you all talking in tongues on this stuff by the end, that's the intention. So this is the title, but what I'm actually going to say is this. So why category theory is the closest thing that I know to a perfect language. I don't think we're quite at perfection yet, but I think this is getting there. So what I really want to do is to try and give you some intuition for what categories are, kind of abstractly. I know a lot of you are really into your functional programming, and maybe some of this is going to be a bit too simplistic for you, but I thought it's good to start with the basics. So if I had to explain to somebody what category theory is all about, and I had like one picture that I could use, it would be this one. So basically, what we have here are these objects, or dots, or nodes, or whatever you call them, A, B, and C. And then you have these arrows. And so these are the basic things that you see in categories. You see objects and arrows. And what I'm trying to indicate here is that if you go on a journey from A to B, and then you go on a journey from B to C, then you can put those two journeys together to get a journey from A to C. And this is really the basic idea of composition, which lies at the heart of category theory. So a question you can ask is, what do these arrows represent? Okay, so we have objects and we have arrows. And what I really want to get across in this, over the course of today, is that these arrows can really represent anything that plays the game of category theory. Now, for you folks, probably a lot of the time, your arrows are going to correspond to functions or processes of some kind. And you can see that this is what I'm trying to illustrate here. So basically, category theory, where you look at things like this more abstractly, is an abstract language for describing composition. And I'm claiming that this is a good language, maybe close to a perfect language. So why should that be the case? Well, it's because a lot of things that we think about can be put in terms of composing things together. So if I say to you, say I need to explain to you how to make a machine, that would be a series of instructions or processes, and if you compose those together, you get the process of making the machine. Or if I say, oh, can you look after my dog while I'm in Zurich? And someone says, oh, how do I do that? I say, well, first you feed the dog, and then you walk the dog. If you compose together those two arrows, then you get the process of caring for the dog. So you can see that it's the same sort of pattern that underlies this kind of scenario as the pattern that underlies this scenario, where we're composing a journey from A to B with a journey from B to C to get a journey from A to C. So what we really do in category theory is to try to only think about the objects and the arrows and how the arrows compose. As much as we can, we try to forget about all the names of all the things involved. And this is really where the power of the theory comes from, because we can talk about all sorts of different things, because we basically forget about the names and only concentrate on the compositional structure which underlies it. So this makes category theory very useful for mathematics, for example. So you can look at, basically, we'll get to this later, but basically different areas of mathematics correspond to different categories. And so let's say you're interested in set theory. Well, then you'll have a category which has objects as sets and arrows as functions. And when you're sort of walking around in the arrows of this category, you're doing set theory, or you're applying functions. It's probably very similar to this category Haskell, I think it's called, which has objects as types and arrows as functions. So that would be doing set theory from a categorical point of view. But maybe you're not doing set theory. Maybe you're a topologist. So then you have this category which has objects as topological spaces and arrows as continuous maps. But the thing is that when you forget about the names of things, you can see a great deal of similarity between what's happening in that category and what's happening in another category. And in fact, the deeper you get into category theory, the more amazing it is that you can see that there are things that really shouldn't look similar at all, like things to do with proof theory and things to do with sets and functions, these kind of categories which seem like they're completely different. And we can see that there's an enormous amount of similarity when we know enough category theory. So again, I keep showing this triangle, right? I'm saying this triangle could be used to describe how to take care of a dog, but a very similar kind of pattern could be used to describe how to compute double the length of a number. So this is maybe a bit closer to functional programming. If you have to write a functional program to calculate double the length of a number, well, you can get your number. I said that wrong. Say you want to write a program to calculate double the net length of a word. Well, you can take your word, you can apply this function length to get a number, and then you can apply this times 2 function. And that's going to give you twice the length of your word. So it's going to send cat to the number 6, for example. But then we can define this purple arrow, double length, to be the composition of the red arrow and then the blue arrow. And you can see that this is the same kind of idea of composing arrows. And we can see here that it can basically be used to describe how you can build up functions, or at least some ways you can build up functions. But the point of category theory is that if we sort of abstract what's going on here, then we get something that we can apply all over the place. In fact, we can sort of even turn these methods of studying things which are compositional back on category theory itself and generate loads of interesting maths that way. So, why might we be interested in this kind of like philosophically? So I'm going to kind of dance around the idea of categories for quite a long time before I sort of show you the definition. So a kind of question we can ask is like, can category theory help us make sense of the world, or can it help us make sense of what ideas are, like in a very general kind of way? And to kind of, I think it can. And to motivate this, I want to ask you a question, which is, what is a chess king? Right? So you know the game of chess. That's a chess king. But what is a chess king? Like, if aliens came and visited and they asked you, what is a chess king? Like, how would you explain it? I mean, you could say in a very flippant way, well, that's a chess king, or a chess king is a piece of wood. But that doesn't really convey the essence of what a chess king is sort of in the world of ideas. So, you know how in social sciences they have this phrase like, you will know a man by the company he keeps? In other words, if you know about the friends someone has and how they fit into the community and things, you understand a great deal about them. Well, in another kind of way, I'd say you know an idea by the company it keeps. Or if you could somehow make a network of different ideas and see all the kind of maps between those ideas, then perhaps you could understand what a chess king is just by knowing its position within that network of ideas and how arrows related to it compose of each other. So this is the kind of thing that I would say is the kind of unsaid story behind category theory, is that to do it or to get into it, one should get into the habit of trying to look at things without directly referring to them. So, for example, we'll come to this later, but you might have some mathematical objects like a set of elements or a network or something, and you can surely describe that thing from an internal perspective. You could say, oh, this is a set of 3 elements, or this is a directed network with such and such a structure. And that's fine, that's the classical way of doing it, but you can also, very often, describe things purely in terms of objects and arrows. So from this latter perspective, that thing that you're interested in is just an object, it's just a little dot. It's just something that you can't actually open up and learn anything about. But if you know about all of the maps or all of the arrows in your category and how they compose, very often you can reconstruct the structure that's internal to that. And this is the kind of game that we play. And the more we play this game, the more we realize how to identify certain mathematical structures, speaking about them from a sort of external point of view in terms of composition. And once we've done that, we get this kind of pattern that we can then import into lots of other places, because it's not defined based on the internal names of things. It's defined externally in some sense. So, yeah, it's a bit of a big claim to say that category theory can help us understand this network of ideas. I don't really think we're there yet. I feel like this is maybe something that's hopefully going to happen over the next 100 years or so, is that people are going to be able to nail down what this really means more. There's a result in category theory called the Yoneda lemma. Now, I'm probably not going to have time to get into it thoroughly today, but if you're interested in this line, like that's the main result to get to. It's just that, like, there's a sort of tower of abstraction that we have to climb up, and I don't want to, maybe it's not so good to introduce everything in one go. Right, so I wrote this slide when I was doing this talk to cognitive scientists to explain what a function is. I'm guessing maybe I don't need to explain what a function is here. So forgive me if this is a bit too simple, but I might as well say everything. So what I want to do is to sort of show you the quintessential example of a category. And I've already kind of said it, it's this category of sets and functions, but I want to make sure we're all on the same page about what this thing is, because it's sort of like one of the nicest examples of a category. And you can view the general idea of a category as a sort of abstraction of this category of sets and functions. So what we have here at the left is this set. So a set is just a collection of things. I'm calling this the set of fruit, and you can see it has these 3 elements here. And then I also have this other set, this set of colors, and this function here. So this function f is just sending like a function f from a source set, in this case fruit, to a target set, in this case color. You just send every element of the source set to some element of the target set. So here I'm sending strawberry to red. So with this function, of course, there's an interpretation of this, right? I'm telling you what colors these fruits usually have. But I could equally well send all of the elements in fruit to the color yellow, and that would also be a bona fide function. So we have sets and we have functions. And we can compose functions. So this is the other key thing. So here we have this other function g, which goes from colors to numbers, and then we can compose these functions in a way which I imagine you all know already. We just do one function, and then we do the other. And that builds this composite function. So maybe here there's some new notation. So you can see that the way I'm getting this purple function here, it's going to be a function from fruit to number, because the f function starts at fruit, and the g function ends at number. And you can see the way we get it is we see so if we want to see where this composite sends strawberry, for example, we see where f sends strawberry, and then we see where g sends that, and we kind of follow the route along, and we see that the composite sends strawberry to number. Okay, that's probably a bit too, yeah. So here's how we look at it from a category theory point of view. Okay, so this is the thing. So what's going on here? We just forgot information, basically, okay? Category theory is easier than set theory in some ways, because what we've basically done to go from this picture at the top to this picture at the bottom is we sort of forgot about the insides of these things. So at the top here, you see we have this fruit, and it's this set of 3 elements, and we can inspect them and everything else. And we have this function f, and you can see exactly how it's defined, what it sends to what. And then when we go to the category theory viewpoint, we forget it, right? We say, okay, actually we just have an object which corresponds to fruit. And we just have an arrow here from fruit to color. And that corresponds with this function. So what we're essentially doing here is only recording what the objects are and what the arrows are. And crucially, we are also remembering how composition works. See, this is the magic. If I didn't tell you that, you would probably just think I was silly with this, right? If I have all this information at the top, which is like high quality information that tells you everything about these functions, and then suddenly I move to the picture at the bottom, you might get annoyed, right? You might think, well, why are you losing all this information? You've forgotten about the internals of these sets and how these functions work. But what is very, very interesting is that if you actually have access to all of the sets and all of the functions, if you have an object for every set and you have an arrow for every function, and you know how those arrows compose, so you know that, like, if you compose the red arrow with the blue arrow, we get the purple arrow and so on. Actually, that's enough to be able to basically reconstruct the meaning of these objects and arrows. So it's quite a non-trivial fact that we'll get to later, but this is the sort of magic of category theory, is that you start being able to do mathematics without actually having to look inside of these objects in some cases. So yes, I'm trying to tell you here about the category of sets and functions. So it's actually quite a mind-blowing concept if you think about it. So imagine, okay, what I'm about to say is really paradox-inducing, but imagine all sets, right? So for every single set, you have an object. And imagine all possible functions. And for every possible function, you have an arrow. And imagine you know how composing each pair of arrows that are head to tail makes another arrow. That's what this category of sets and functions looks like. And this is our sort of quintessential example of a category. It's like the nicest one in some sense, because basically it represents what's going on in set theory. I'm going backwards. Oh. Okay, right, so that's enough dancing around the... Maybe I'll do a little bit more dancing around the definition of a category before I actually show you it. So, can people put their hands up if you've heard of a directed network or a directed graph? Okay, right, so what a category is basically just a directed network plus a little bit of extra information. That extra information is really how you compose arrows. So I'm going to give you the kind of nice informal definition of a category, because usually when you see this in textbooks, they'll kind of tell you this, but then they throw in some extra rules, and those extra rules are really there to make life easier, but I think on a first viewing they they look complicated. So I'll tell you again, basically a category is just a directed network with this idea of composition, which means that if I have an arrow from A to B, and I have an arrow from B to C, then there must be an arrow from A to C, which is considered to be their composition. And when you're defining a category, you have to tell people how that works, because there might be many arrows from A to C, so you have to say which one is considered to be the composition. And that is the essence of what a category is. There are some extra details, but if you understand this idea of composing things, this idea, that if you have an arrow from A to B, F, and you have an arrow from B to C, which is called G, then there exists this arrow, which we call G after F, which goes from A to C. This is the core of category theory. Apart from this, there's just a few extra rules which make life easier. But this is the basic idea. Yes?
So when you say there exists a G after F,
yes.
Is G after F the name of this, or is this or after, is that an operation as well? So how do I think of that?
You should think of it as an operation, I think. I think that the best way to think of it is to imagine that you start off with a directed network. So if you want to define this in a computer, maybe you'd say I have a set of objects and a set of arrows or directed edges. And then you say, okay, for every arrow, I have a source object. So that would, maybe you'd use a function to define that, send every arrow to its source object, send every arrow to its target object. So basically, you've recorded where the head and the tail of each of your arrows is. And then on top of that, you want to record how composition works. So you want to say, the way I would do it in a primitive way, I would make a big table, and I'd say, okay, whenever I can compose these two arrows, I have to say which other arrow is considered to be their composition. And so you could consider this, this circle here. So when you see this circle, in your mind, you should think of the word after. Okay, so this is G after F. So it means that first we do this arrow F, that gets us from A to B, and then we do this arrow G, and that gets us from B to C. But it's really an operation, yeah.
And this would mean that this operator, this after operator, it's pure coincidence that's the same for functional composition as well, when we say G of F. Can you please repeat the question, because I don't have a microphone?
Yeah, no, so the question is, when we have G after F, is it a pure coincidence that means function composition? To my mind, I would imagine that you already have like a list. Maybe we're violating some Russell things, but we have like lists of all of the functions and lists of all of the sets and things, and then we'd consider that to be a sort of operation, that if we do this operation +1 after +2, that equals +3, or something like that. Okay. So yeah, this is the kind of the idea at the core of category theory. Are there any other questions about this? Okay. So this is a nice picture to sort of describe what's going on. So the point here is that we want to define how composition works. So you see here with this red arrow and this blue arrow, see how the blue arrow starts where the red arrow stops. So these are head to tail. That means they can be composed. That means we must define how the composition works. But look at this picture here. There are two arrows which start at A and end at C. So which one should be considered to be the composition? G after F. We have two possibilities. So we're going to have to actually specify which of these arrows is the composition. And in doing that, we define what a category is. Okay, so that's the basic idea. Now I'm going to add on a few of the kind of bookkeeping or I don't know, I shouldn't really call it bureaucratic, but it kind of feels like this is the core idea. And then basically mathematicians discovered that if we make a couple of extra constraints on what these kind of structures should be, they end up being much nicer. They end up living in a nicer place in the mathematical universe and being easier to work with and so on. So on top of what I've already said, we're going to have two extra constraints. One of them has to do with some special arrows which we're going to assume exist. And these are called identity arrows. So what we're going to assume is that for every object A, we have something called an identity arrow. So if you're in this category of sets and functions, this would be the identity function. More generally in a category, you should think of these identity arrows as sort of, you should think of them as do-nothing operations, okay? So what kind of features do these identity arrows have? How do we use them? What do they do? Well, they are defined to have the property that if we compose something with an identity arrow, the result is always equal to that thing. That's the sense in which they are do-nothing operations. So if we compose an identity arrow after f, as you see in the top picture, you see the answer is f. So when I write this diagram here, this is another thing which is very common in category theory, is this idea of so-called commuting diagrams. Commuting diagram is just where you draw a load of paths that you can make out of arrows, and then when you say this is a commuting diagram, it means that whichever path you take, when you compose the things around that path, you're going to get the same answer. So when I draw this triangle at the top here, and I say this is a commuting diagram, what I mean is that if I do this arrow f from A to B, that's equal to the arrow I get by composing f and then identity B. Or if you like, doing identity B after f equals f. So this diagram here denotes this equation, corresponds with this equation here. So this is another reason I like category theory, because I like to see pictures of maths instead of just equations. Yes? Yes. Yes, there can be and there must be. The question is, can there be an identity function for every object in the category? And also, in Haskell, would this correspond to an identity function? And I think the answer to both of those is yes. In general, in a category, they can be very specialized because, like, if you have this category of sets and functions, then your arrows are functions. And so in that case, your arrows are sort of like processes and you're composing them. But there are other categories where things look very different. Yeah, maybe I'll do. Not sure whether to do it now. Yeah, I think I'm going to do it now because, like, this is something I find people, like, it's very common to think of these arrows as maps or processes or functions. And another word people have for arrow is this word morphism. I don't really like the word morphism very much. I find it encrypts the subject even more than it is already. But what I want to communicate is that arrows don't have to be of that nature. An arrow can actually be anything that satisfies the axioms of category theory, if you like. I'll tell you what, I'll finish the full definition of a category, then I'll show this alternative example. But yeah, so identity, yeah.
So is the identity function on one object unique?
Yes.
Yes, it's always unique. Okay.
Yeah, it is.
Can you repeat the text for the record?
Oh, yeah. So you're asking if the identity is unique on a particular function.
An object.
Sorry, on an object, and it is. So a way that you can see this is that if there were two identity functions, then you would have a problem because they would have to have the feature that if you compose them, they give an identity, but which so yeah, it has to be unique. So it's really just saying that you have these special arrows and they have this property that whenever you can compose them with something, before or after, that's enough to nail down these arrows uniquely. And this is a sort of reoccurring theme in category theory, is that people come up with definitions which really nail things down kind of almost completely without having to look inside things too much. So this is identity. The final part of definition of a category is just another thing to make life easier. So I want to ask you a puzzle now. I've explained that we should have a notion of composition, right? So I say when we have G and F at the top here, be like, oh, okay, well, G starts where F stops. They are composable, so we can compose them. And we have a way of composing them. Now I'll ask you a problem. You see at the bottom here, we have these arrows F, G, and H. And my problem for you to think about is how are you going to compose those together? Can you compose all of those arrows together to make an arrow that goes from A to D? So if you think about that for a moment, you might think, well, actually, there's two ways that I could proceed, right? Because I only told you how to compose like two arrows that are head to tail. But here we have a chain of three. So how do you do it? You could start by composing F and G. Oh, I haven't. Okay. Yeah, you could start. Maybe I need something to. Okay, let's do it like this. You can start by composing F and G. And that would give you an arrow that starts at A and ends at C. You see that? And then once we've done that, which would correspond to doing what's inside this bracket, well, after we've done that, we can then compose that with H. That's one way we could do it, right? We could start by composing the red and the blue first, get the result, and compose it with the green. Or we could do it a different way. We could start by composing the green and the blue first. So then we'd be evaluating this, H after G, and then we'd compose that with F. So which way are we supposed to do it, right? Like, I tried to tell you how to do category theory, and we've suddenly reached this place where we don't know what to do, right? We have these three things. We could compose these two first, and then this one, or we could compose these two, and then compose with the red. Which one should we do? The answer is it doesn't matter, okay? So our final rule to make life easy for ourselves is to say that whenever we have a situation like this, it doesn't matter which order we do it in. In other words, arrow composition is associative. And you might have seen other examples of things like this. For example, in addition, right? Like if say I have to add up 1, 2, and 3, I could do 1 plus 2, and then I can do plus 3. Or I can do 1 plus open bracket, 2 plus 3 close bracket. And nobody writes these brackets because there's no point, because everyone knows that it doesn't matter. Not the case if you're doing division, right? If you have a divide by sign, then it matters where you put your brackets. So in a way, division is more complicated, too complicated for category theorists. So we make life easy for ourselves, and we assume that arrow composition is associative. And what this means is that I can just write H after G after F with no brackets. And that's not ambiguous. Much as with function composition, right? Because the category of sets and functions is a category, therefore function composition is associative. That's quite a backwards way of looking at it, but yeah. So that's it. That's the definition. That's the definition of a category. Yeah.
So this means, but these things are properties that the composition operator must satisfy.
Yes, exactly. So if, like I just said, one intuitive way of getting a grasp on a category is to say that it's a directed network plus this idea of composition. Another way that you can get at the idea of a category is to sort of think about composition first. So if you think about this idea of a group in maths, or more generally a monoid, there you have a notion of composition, or sometimes it's called multiplication. And a monoid is a special kind of category, and you can think of a category really as sort of like a monoid, but it's a monoid where you can't times any element by any element. You can only compose arrows when they're head to tail. So you could say it's a sort of partial monoid, where you can't just multiply anything by anything. When you can multiply stuff is kind of described to you by looking at where these arrows start and stop. Yep.
Let me, just one. Excuse me, maybe for a longer one, I should maybe run around with the mic, sorry.
Yeah, so, is on? So if you have a set of objects and arrows, but say they don't contain a function, IDA, IDB, they are missing some of these functions.
Right.
It means it's not a category.
Yes.
And as well, if, say, you define what the composition is, but it turns out it's not associative, you can say that it's not a category.
Correct.
Okay.
Yeah, that's right. I mean, people consider these more general structures, but they're not called categories.
And so IDA, IDB, all of these are part, or is just ID that is part of the starting set?
So you have your set of objects, and you have your set of arrows. Within your set of arrows, for every object A, there's a special arrow called IDA.
Yeah. Okay, thank you so much.
So it's okay to have multiple arrows, I assume, between, let's say, A and B.
Yes.
But
excellent question, yeah.
In these examples, you're just referring to one of those possible arrows. You're not referring, like F doesn't refer to all possible paths from A to B, it just refers to one specific one.
Exactly. Okay. So the set of arrows from A to B, it's sometimes called the HOM set. There's so much terminology, but HOM set is like, HOM is short for homomorphism. So morphism, arrow. So yeah, in general then you'd have a set of arrows from A to B, and there could be many. You can have many arrows from A to B. You can have arrows going in both directions. You can have many arrows going from an object to itself as well. Like there are many functions from the set of numbers to the set of numbers, and there'll be arrows from this object of numbers in the category of set to itself. So it's loopy. But
morphism is just one of those arrows in proper terms.
Like, yeah, so the word morphism to me is it's just synonymous with the word arrow.
Okay.
So, but that is F. That is one particular arrow or morphism from A to B, or you could say in a fancy way, it's a member of the HOM set of arrows from A to B. But yeah.
Thank you.
Yeah.
Thanks. So does every object in the set, for it to have to have an arrow either at the tail or the tip of the arrow? Does it have to be connected? Or can you just have like orphan objects in your category?
Can you just have what, sorry?
Like orphan objects in your category that don't have any arrows either coming from them or to them?
Yeah, you can have awful objects, but you have to have identity arrows. So if you say, I want to have 5 objects, but I want to have as few arrows as possible, well, you're going to have 5 arrows, right? Because say your objects are 1, 2, 3, 4, 5, well, 1's going to have an identity arrow, which is just like a little self-loop. And 2's going to have an identity arrow, which is a self-loop, and so on. So if you think about that, you can see that the idea of a set is kind of like a special case of the idea of a category. So like these 5 objects, this awful category, which only has identity arrows, it pretty much looks like the set of 5 things, right? And then, so yeah, we'll come to that a bit later, but yeah.
So one quick question. So consider the function that doubles a number. I can implement it in 2 ways. I say number plus number, which is one of these arrows. And what about times 2? The number times 2. Are these now 2 arrows, or is this 1 arrow?
1. They'll be equal.
Because the start and end are always the same.
Well, I mean, if you have 2 functions in set that both start at the same set and end at the same set, and you can show that they work the same for every input, then they must be the same.
Got it. But this relies on the semantics of sets, basically, and functions on sets.
Yes.
Got it. Okay, thanks.
Yes. So that you would indicate that kind of thing by a commuting diagram. But yeah, okay. So let's have a look at some examples then. I think I'm gonna. Okay. Yeah, let's talk about this one. This is a nice, interesting one. So what I'm showing here, like for a start, let's not think about it with categories. Let's just think about this in arithmetic. Okay. So this is like a system that you could play games with if you're so inclined. You have 2 numbers, 1 and -1, and you can multiply them together. That's all it is, right? So this is an example of a monoid. Okay, we have these 2 elements here, and we have this operation. Now, I'm writing this operation as a circle here, and you can probably guess why, but on a first viewing, I would encourage you to think of that circle as meaning multiply. Okay, so 1 times 1 is 1, -1 times -1 is 1, and so on. So I could just give you that. I could say, okay, I'm talking about a monoid. It has these 2 elements, 1 and -1, and it has this operation, and you'd probably be happy with that. There's an equivalent way to define this, which is as a category. So what I'm trying to indicate here is that this setup also corresponds to this category here that I'm picturing at the left. So these elements, like 1 and -1, are now corresponding to arrows from this object dot here to itself. So what am I drawing here? I'm drawing a category. So remember, a category, it has objects and arrows. Yeah, and I'm saying that thing in black is a category. So what are the objects? What are the arrows? And how does arrow composition work? They're the 3 questions you should always ask whenever someone tells you about a category. You should always ask them, tell me the objects, tell me the arrows, tell me how composition works. So what about this? What are the objects? Well, there's just one object, and I'm just going to call it dot, because I don't have to give it another name. What are the arrows? Well, there's 2 arrows. I'm calling them 1 and -1. And how does composition work? Well, I want composition to work in this category exactly as I've written in red. Okay? So if I compose my 1 arrow with my 1 arrow, in other words, if I do 1 after 1, I want to get an answer of 1. So I want arrow composition to work there just as I've shown. And in fact, you can see here, if you inspect these rules, you can see here that when I time something by 1, it's not going to change it. So composing with this 1 arrow doesn't do anything. So can you guess what kind of arrow 1 is? Anybody? Identity. Yeah. So we have an identity arrow. So that's ticking one of our axioms of a category. We have an identity. You can check in your own time that this is also an associative operation. And so this is an example of a category. And I forgot who asked it, but we were talking earlier about, are there cases where arrows might not correspond to functions? Well, here's a case, right? These arrows correspond to numbers. These are not processes or anything like that. These are just elements. But they satisfy the rules, they satisfy the laws of a category. And in fact, any monoid, or all, can be thought of as a one-object category. So if you have any monoid, you know, a monoid is like you have this set of elements and you have this way of multiplying them. You can always encode that as a category. You just think of each of those elements as an arrow from a single object to itself. And hey, if you have any, like let's say you have a category of one object, well, that means you can compose any pair of arrows, right? Every arrow, if my only object is this, well, every arrow sort of has to start here and end here. So I'm going to get dizzy if I keep doing that. But that means you can compose anything. So you can see that a monoid, in fact, a monoid is precisely the same thing as a category of one object. So that's where we start to see the kind of wisdom of behind the definition of a category. This is another example of a category. Here, to make this example, I take a set. So this is maybe something a bit different for you functional programmers. Like, I take this set with two elements, 1 and 2, and then I want all the subsets of that. You can do this more generally with any set, but my objects are subsets. So what are all the subsets of this thing with two elements? Well, we've got the empty set here, the set with just number 1, and the set with just number 2, and the set which has both 1 and 2. And now my arrow is indicating that the first set is contained in the second set. Right? So I'm telling you how these subsets are contained within one another, but I'm doing it with a category structure. So here again, we see some kind of new thing happening that you might not have seen before in a category. You see, when you're doing functional programming, you're probably more interested in this category of sets and functions. So if you have two sets, like the set of numbers and the set of words, there's loads and loads of functions. From the set of numbers to the set of words, there's loads and loads. But here, we only have either no arrows from A to B or one arrow from A to B. We don't have more than that. So this is like a simple case of a category where everything works more easily because, you know, basically you don't have to tell people how composition works in as much detail because we know that there can only be at most one arrow that, yeah.
But excuse me, why is there just at most one arrow? I also have the identity arrow there, right?
Oh yeah, I haven't drawn those. Yeah, so, yeah, it's a good thing that you're pointing this out. So as time goes on, you'll see maybe notation degenerate and people stop drawing things. So it's good to point things like that out. So it's often the case that people don't draw the identity arrows. Yeah, another thing you'll see, by the way, is that this circle thing, meaning after, that's very often omitted in the text. So people will just write GF instead of G after F. Yeah. Yeah?
I think it's important to point out that you could add 2 before the whole atom or after the whole atom. Get different for 1, 2 or 2, 1.
Yeah, like what I'm indicating here is just which of these sets are contained within one another. So I'm wanting to think of these as sets. So I'm trying to say that like the set with just number 1 in it is a subset of the set with 1 and 2 in it. And that's what the red arrow indicates. Yeah. Yeah, so there are a few examples. I guess I'm gonna zoom out a bit. Why am I interested in category theory? Let's talk about things more generally. So I was a mathematician for about 8 years before I discovered category theory. And then once I did, thanks to Bartosz Malowski's great videos, which I would recommend to you folks, especially knowing Haskell. I think it's a great way to get into it. But yeah, once I discovered it, I was just like, I was almost angry really that no one had showed me before because it seemed like it revealed so many connections between subjects that I hadn't kind of noticed before, or that I thought, oh, you know, there's got to be something here, but I don't know what it is. And then, like, category theory is kind of hard to learn at the beginning, but once one gets beyond a certain threshold, it's just such a rush to be able to see the connections between these things. So I like this picture here. I can't remember who drew it, but it's a sort of playful depiction of mathematics, right? Like, I kind of think of maths like a big shape or a landscape or something, and it's well depicted here. You know, we're depicting these different regions, like we've got the tundra of topology and the ocean of logic and these different places. And you can see that the category here is sort of depicted as this kind of moon above the landscape. And I think it's a good kind of metaphor because it is a bit abstract. Like, there are people that call it things like abstract nonsense. So, you know, it is a bit, and honestly, it sometimes can be in danger of floating away. Like, I know some category theory people that just like to think of things on such an abstract level that you kind of wonder if they're ever going to make contact with the ground. But on the other hand, it kind of gives one the ability to look down and see connections between different areas of mathematics, which in really quite a special way. So, so far, I spoke about the category of sets and functions, right? And we say, okay, the objects are sets and the arrows are functions. So there's this word object. And I think it comes from the idea of like a mathematical object. And so if you're doing set theory, your objects are sets. If you're doing group theory, your objects are groups. And if you're doing group theory, you're interested in maps between groups. They're sort of like special functions that preserve structure in a way that I'm not going to go into. But that's what you'd study there. Now, what's really, really mind-blowing is that there are maps between categories, okay? So you have all of these different categories, but you can also, just like you can do a function from one set to another, there's this idea of something called a functor, which is like a map from one category to another category. And that allows you to compare these categories with each other. And it allows you to say things about how they're related, right? Like, if I tell you I have an injective function from the set with 2 elements to the set with 3 elements, I've told you something about the properties of those sets, right? You know that the second set has at least as many elements as the first one. So having maps tells you things about the objects, and we can study maps between categories. And it turns out, in fact, that there's a category of categories, right? Your objects are categories, and your arrows are functors. And this is wild. Like, it really lifts one up to a whole new level of abstraction. It's pretty cool. Yeah, so this is a rough idea of what one of these functors is. I'm just going to scan ahead so I know what's coming. Yeah. Okay, yeah. So this is this basic idea of a functor. I think I'm going to stop for a little break soon. I don't want to overload people in one session. But basically, the idea of a functor is that, so we have this category C, okay? This is another thing you'll find in books and things. People usually draw these pictures of categories, and they just look like directed graphs, right? People often don't draw identity arrows, and they often miss out a lot of the information. And I think another thing that's a bit confusing for people first starting category theory is that people usually don't tell you explicitly how composition works. So usually if you see a picture like this one here in black, I don't want to say it's a hard rule, but it's usually a sort of unwritten rule that, like, this black arrow here is the composition of the other two. You know, if you go along this arrow and then you go along this arrow and you compose them, you get this arrow at the bottom. So that's one thing. But what I'm trying to illustrate here is that we have this category C, and we have this category D, and then there's this thing called a functor, which is basically, it's telling you how, it's a way that you can send the objects and the arrows in C into the objects and the arrows in D in a way which respects the basic structure of the category. So, yeah, I'm just going to say that the rules this thing should satisfy briefly, but after the break I'll spell it out more precisely. But basically, okay, so to understand this idea of a functor, firstly, let's just forget about composition, right? Let's just pretend that this is a directed network, okay? So we have these vertices and these directed edges, and then what's a good notion of a map between directed networks, right? So I have this directed network C, it has objects and arrows. I have this directed network D, it has objects and arrows. What would be a good notion of a map from C to D? Well, I want to send the objects of C to the objects of D, and the arrows of C to the arrows of D. That's what I'm trying to indicate with these dotted things. But, you know, I want this map to respect connectivity, right? Like, I have this vertex here is touching this arrow here. So after I've mapped these things, I want the image of this to touch the image of this. You know, it wouldn't make much sense if I had like an arrow that's connected to this, and then these two things go over here, but this arrow goes somewhere totally different, right? In other words, this map should preserve connectivity. The other thing it should preserve is composition. So if I have two arrows and I compose them and then I map, then I'll get the same answer as if I map and then compose. That's another axiom that we insist on. And finally, it should send identity arrows to identity arrows. So that's the idea of a functor. Yeah, we're gonna nail this down better in the future. But what I wanted to just indicate here, because this is like, I don't know. When I saw this was the point that my category theory addiction began, is this idea that there's this category of categories, which is endearingly called cat, and you can see that the actual objects of this thing correspond to categories, and then the arrows are corresponding to functors. So this is showing us all these different ways that we can convert between mathematical structures, and the whole thing in itself is another structure. Now, I know that there are counting issues here, right? Like, someone's probably going to tell me that I should have, you know, like I said, okay, a category has a set of objects and a set of arrows, and actually I should be using classes or something, so I'm not talking about the set of all sets and things like that, but I'm gonna ignore that. But yeah, this is the idea. So, yeah, how long am I in?
A little bit more than an hour.
Well, that's a great time for a break then. Yeah, so I'll resume again in 15 minutes, and yeah. This one, yes.
Yeah.
I wanted to clarify here, someone said, and it's a good point, that I should clarify here that the arrows here, like if there's an arrow from A to B, you should read that like A is a subset of B. So the arrows here denote containment relationship. Yeah.
Cool. Any other clarifications? I have two microphones. I'm just going to distribute them so that I don't have to do the running around, so at least half the time.
Thank you. So if you could go back to the slide you were just showing. So unfortunately, I got a bit lost here. Could you summarize the takeaway of this slide? Because it just reminded me of lattices, and at that point
That's what it was. Yeah, that was what I was going for. Yeah, so I think I'm a bit guilty of not following my own recommendations with this, which is probably why it's confused people. So, like I say, if someone tells you something is a category, you've got to ask them, what are the objects? What are the arrows? And how does arrow composition work? So in this case, the objects are the subsets of this two-element set. So I have this set with two elements. You know, I should probably write it like, maybe I'll try and write the same thing a little bit more traditionally. So we have this set here, you know. It has the elements of 1 and 2. And then we're going to write all the subsets of it. So this is the subset with just a 1. This is just a 2. And this is the empty set. So these are the objects. We have 4 objects. Next question is, what are the arrows? So I'm going to have an arrow from, yeah, go.
Sorry, I have a question which might be obvious or stupid, but so I understand that the axiom is that a set contains the empty set, because you just draw the empty set on the left-hand side. But at which point did we establish that axiom?
So I'll define. I'll say that set A is contained in. So let's say we have A and B, and these are both subsets of 1 and 2. So I want to say that by definition, A is contained in B, if and only if, for all A in A, we have A is also in B. And if capital A is the empty set, then this is true like vacuously. Yeah. And so, and also in this case, this is also the necessary and sufficient conditions for there to be an arrow from A to B. So if I draw this in, that's 1 is a subset of 1, 2, so I need to draw an arrow. 2 is a subset of 1, 2, so I draw an arrow. And like I say, the empty set is contained in anything. And so I've told you now, and also, as Farhad said, there should be identity arrows, right? Like you could say, this set is contained in itself. This set is contained in itself. So I should draw these as well, but they're often sort of omitted. And like I was saying, it's not just what are the objects and the arrows, we also have to say how arrow composition works. You know, this is the final part of, so I could ask, okay, look at this arrow and this one. I can compose those, right? Because one arrow stops where the next one starts. So there should be a composition of these two arrows. So there should be some arrow which starts here and ends here, which is considered to be the composition of these. Now in this case, there's only one such arrow. So I can save energy. I don't really have to tell you what I get from composing this with this, because there's only one possibility. And this is quite a subtle but important idea, because there's some other kind of structure in mathematics called a pre-order, or a pre-ordered set. And in fact, a pre-ordered set is exactly the same thing as a category where you don't have any parallel arrows. Like, if you have a category that has a feature like this one does, where if you pick any two objects, there's only two possibilities. Either there's no arrow from A to B. Like, for example, there's no arrow from here to here. That's one possibility. Or there's exactly one arrow. If you have a category which has those special features, it corresponds exactly to a pre-order. So category is sort of in this sweet spot in mathematics where it generalizes the notion of a pre-ordered set, because this category without many parallel arrows corresponds to a pre-order. Such a thing is also called a thin category, which I think is quite a good name for it, because it, You know, the set of arrows from A to B is either empty or a singleton. So category generalizes pre-order. It also generalizes the idea of a monoid, because as we saw earlier, a category of one object corresponds to a monoid. So if you, like, I know it's a lot of new ideas, but if you get your head around those two, like, you're really on the way to understanding, like, the categories, yeah.
Thank you.
Okay. I know there were more questions before. Yeah.
I have two questions. So the first one is actually related to this. What happens if you take the true subset so that you no longer have an identity? This means that it's not valid anymore?
If you take the what subset?
The true, so without the line on the bottom, so that A is a real subset without a proper subset.
A proper subset, yeah. Yeah, exactly. If you can define a math structure where there's an arrow from A to B if and only if A is strictly contained in B. So you get rid of the line. But that, as you said, that would not be a category, because then you wouldn't have an arrow from A to A.
What would that be? Is it anything special, or?
I think it's called a weak category or a quasi-category or something. But yeah, it's not an ordinary category. Like, the idea of identity is quite important in category theory. And the reason for that, so this is another thing that people ask when they first see categories. They say, why do we have identity arrows? Right? What's the point in them? If just composing with an identity just gives you back the other arrow that you compose with, then why bother with that idea? And my answer is usually, well, why do we have 0 in arithmetic? It's the same kind of idea. It's really useful sometimes to be able to talk about a do-nothing operation. You know, like if I add 2 and then I take away 2 and then that's 0, or well, we'll see this later if I have time to get onto it, but this idea of identities is useful, yeah.
I have one more question. Could you go back to the slide? It was one of the other ones, I think.
Higher?
After lower, afterwards. Where you were talking about the functor already.
Yeah. Too many things.
That one. So you mentioned, so I'm looking at the left circle category.
Yeah.
You have the arrow going up to the dot at the top, and then the arrow coming back down on the right. And you,
like here, yeah?
I mean, those two exactly. And you said something along the lines of these, when you compose these two, it gives you the arrow on the bottom.
Yeah.
So my question surrounds kind of the notion of equality of these, are these two composed arrows equal to the other arrow? Mm-hmm. And at the same time, what happens if you have multiple arrows on the bottom? To which one of those arrows is the composition of the two on the top equal? Mm-hmm. And what happens if you have a cycle? Does it mean that once you get back to the original object, does it have to be equal to what you had before? Okay, so if you have a cycle, then they're like a load of arrows that you compose together, and they're going to make an, so let's call this arrow at the bottom left L, right? It's L for left. So if we had a cycle of arrows and we composed them, that would make an arrow from L to L. Now, that won't have to be an identity in general, right? So in general, if you have a load of arrows that compose to make an arrow from an object to itself, that doesn't have to be an identity. Now, if we draw a picture of it, that might correspond to an identity. If people are good, they usually mark their diagrams when things are supposed to commute. So what I like to do, if I remember to do it, is when I draw a diagram, so let's say I'm trying to indicate that if we do F and then we do G, we get H, okay? So in other words, what I'm trying to say here is that H is equal to G after F. Now, if I'm being good, I'll normally write like a little equal sign or something in there.
And what I'm trying to say here is that this is a sort of commuting diagram, right? So if we look at this region here, and we look at two paths that we can walk around this region, then those paths, if we compose the arrows on those paths, we should get the same answer. But this is just a sort of graphical notation to denote that we'd have an equation like this.
That would imply to me that a cycle is equal to the identity.
Yes, if I drew a picture, if I wanted to show that, I could draw a picture, for example, like this. I could say if we do F, and then we do G. Okay, so the way I'd probably draw it is like this, actually. If I want it to be fancy. I'd say if we compose like that, you see that's making an arrow from A to A. But I can also have the identity arrow from A to A. I sometimes draw identity arrow as dotted, but that's kind of meaningless. It's just to help people see that it should be an identity arrow. But then if I put a little equal sign here, I'm saying that if we do this, and then this, and then this, it has the same result as this. So I'm saying that self loop that you can make by composing those things, in this case, equals the identity. But in general, it won't have to, but it does in this case.
Okay, so what I'm getting is that in general, there's actually no implicit, or maybe there's some relationship between the composition of arrows and a different path, but only if you say that it's a commuting diagram.
Yeah, exactly.
Okay. And if it's not a commuting diagram, then what's the relationship between those arrows then?
Could be anything.
Okay. So, okay.
Yeah. It's like you could do a function from numbers to words, and then a function back from words to numbers. It doesn't have to be an identity, but it could be.
Thanks, I guess.
Yeah. Yeah, okay. So where were we last time? I want to try to get the big three from category theory. So I think so you have this idea of a category. Of course, that's important for category theory. And then people always say about category theorists, like, whenever we hear about some kind of mathematical object, we always want to know what the maps are for that object. So it's this kind of eternal striving for something more general, right? If someone tells me this idea of, I don't know, what a graph is, then I'll be like, okay, what's a map between graphs? And, you can kind of keep asking this question. So if I say that categories are important, then I should tell you what the idea of a map between categories is. And this is this idea of a functor. So I think I'll show you the picture first, and then we'll look at the kind of text-based definition of it. So I hope my writing isn't too messy. Okay, so what am I trying to indicate here? We have this category C, and we have this category D. And I'm trying to tell you what is the definition of a functor capital F from C to D. And so, you know how you have a function between sets, and that'll send the elements in one set to the elements in another set? A functor is basically the same idea, but for categories instead of sets. So a set just has elements. It just has one kind of thing, which are like the elements of the set. But a category has two kinds of things. It has objects and it has arrows. So actually, a functor is really two functions. A function telling you how to map the objects, and a function telling you how to map the arrows. Now, if we call this functor F, we say it's a functor from C to D, it's really a pair of functions. Okay, it's a function that tells you how to map the objects of C to the objects of D, and a function that tells you how to map the arrows of C to the arrows of D. Now, it's a bit confusing. Sometimes we just write F for both of those functions. Maybe you Haskell people are used to this, but yeah, so that's basically it. It sends the objects of C to the objects of D and the arrows of C to the arrows of D. But it has to be sort of sensible in some way, in a way that you'd probably come up with yourself if I asked you to sit down for a while and think about what's a good idea, what would be a nice notion of maps between categories. So what are the important things in categories? Well, objects and arrows. Of course, these arrows have to have source and target objects, right? Like every arrow, it's kind of like almost too simple to say, right? But obviously every arrow has to start at some object and end at some object. So there's some notion of objects and arrows kind of touching each other. And we want our functor to preserve that. Okay, so you see here, this little g here, this is an arrow from B to C. Well, after we apply the functor, we want the image of that, which is over here, f of g. We want that to go from f of B to f of C. So if you have an arrow, so this is an arrow in your category C, and you want to know what's going to happen to this when you apply a functor. Well, you know that it's going to end up being some arrow over here in D. But also, if you look at this arrow, you can say, okay, the source of it is this object. And this object's going to go somewhere when you apply the functor. Well, it better go to the source of wherever this arrow goes to. I mean, that's just how we define it, but it's a good idea. So that's law number one, if you like, that your functor should preserve incidents or things touching each other. A more sophisticated way to say it is that if you have an arrow, then it's going to have a source object. You know, like this arrow here has this as a source object. And we want the image of the source to be the source of the image. Image of the source to be the source of the image. Similarly, we want the image of the target to be the target of the image. It's all just this kind of intuitive idea that your functor should preserve incidents. The other thing I'm trying to indicate here is that your functor should preserve composition. Now, this is a bit more subtle, but it's very important. So, I mean, if you've seen things like group theory, you have a similar thing in group theory, like this idea of a map between groups. It has to have this feature that if you sort of compose things and then you map, you get the same answer as if you map first and compose later. This is what we're going for. So I think I've got it written here with a bit better notation. Right, so these are the laws that we want our functor to have. So I'm spelling it all out here. So let's go through this. So we have a category C and a category D. We're defining the idea of a functor f from C to D. Now, we'd probably write this kind of thing like this, because we like to think of everything as arrows. So it's like an arrow from C to D in the category of categories, if you like. But don't worry about that now. I'm just telling you the proper definition here. So I'm saying that how do we get one of these functors? Well, we need a function sending the objects of C to the objects of D. I'm calling that f. I'm calling everything f. We also need a function sending the arrows of C to the arrows of D. And we need this, which basically means that, you know, the image of this arrow here starts at f of A and ends at f of B. This is just what I was saying before. You know, image of the source is the source of the image of the target is the target of the image. And then the other thing is that composition should be preserved. So let's suppose that in our original, okay, let me just copy this somewhere fresh. Yeah, so let's suppose that we have our category C here, and we've got a couple of composable arrows in here, like that. Okay, and here's our category D. So we want to define this functor. So we better send this arrow G somewhere. We've got to send it somewhere in D, because we're trying to define a functor. And I've already kind of told you that we have to basically have it so that the image of G, which is called f of G, it better go from f of A to f of B. And then similarly, this is going to work like this. But a question I can ask now is, okay, what do I get if I compose these two arrows? Okay, that's what I want to know now. I want to know what do I get if I compose these two? And I can make up some notation for that, right? I can sort of tautologically, I don't think that's a word, but anyway, I can just sort of say, okay, I'm interested in the composition of these two. So, you know, I can say this is f of h after f of g. I'm just saying what I'm interested in. But I actually want to get this. And it turns out that the law, one of the laws behind a functor lets us do this, because we always insist that this is equal to the image of h after g. In other words, if we want to find out what this baby is, we can compose these two, and we can get this, which is h after g. So yeah, this commutes. And then we can see where this gets mapped under our functor, and it will get mapped to the same thing. So the image of the composition is the composition of the image. And then the final law of functors just says that identity arrows are preserved by the functor. So if we have an identity arrow, like this one here, this is identity A. Where does that get sent to by our functor? Well, we know that A is going to get sent to f of A, so this is going to get sent to the identity of f of A. And this is our final law here. So to reiterate, a functor is telling you how to map your objects, how to map your arrows, and then there are these conditions. Basically, that incidence or touching of arrows and objects has to be preserved, and composition has to be preserved, and identities have to be preserved. So that's probably the big hurdle in learning category theory, is to get one's head around the idea of a functor. But it's worth it, I think. It's a very powerful idea. Do people have questions about it? Yeah?
Wait a minute.
Can the target category of the functor contain extra objects and extra arrows?
That's a great question. Yes, it can. It can. Much like if you have a function from A to B, you don't have to hit everything in the set B. In a similar way, you can have a functor, say from a category A to a category B, and you don't have to hit all of the objects or the arrows in the target category. So the answer is yes. In fact, there's a functor that you can always define, which really doesn't hit very much at all. You can send, if your target category has an object, like it might have many objects, but let's just say it has an object X. It might have more things than X, but we can always get a functor where we send all of the objects in the source to X and all of the arrows in the source to the identity of X. And this is like very much not hitting everything in the target in most cases. Yeah.
Thanks. A quick question.
Yeah?
The other side of this question would be, I can always have a very trivial functor that maps to a category with just one object and one...
Yes.
Okay.
Exactly. Okay. And this is a very deep observation. Similar to how you can always have a function that goes to a singleton set. And we have a special name for these kind of objects that have this property that there's always one map into them from anywhere. They're called terminal objects. And they are one of the things that we can detect in a purely kind of categorical way. And actually, I was speaking earlier about this potential to sort of know what's inside of sets or graphs and things without opening the box, as it were. And terminal objects happen to be sort of the key to doing that.
Thank you.
Yeah.
I'll talk really loud.
No, you can't. No matter how loud you talk, the people at home will not hear you.
Got it.
So you mentioned that it has to preserve the structure, but I know it's not a lecture about Haskell, but in Haskell I've only seen ones that trivially preserve the structure, like maybe functor would trivially turn ints into maybe ints, strings into maybe strings. Are you aware of any case where there is some collapsing or expanding or something non-trivial?
Yeah, like if you consider general functors, you can definitely lose a lot of information. So, for example, you have the category of sets and functions, and you have the singleton set, set with one element. Mm-hmm. Let's call that 1. You can have a functor from the category of sets and functions to itself. So that means that every object in the category of sets and functions, every set, has to get sent to a set. Every arrow in the category of sets and functions, every function has to get sent to a function, but satisfying the functor laws. But what you can do is, just like the gentleman before was talking about, you can send every object in set to the singleton set, and every function in set can get sent to the identity of the singleton. So that's a very lossy kind of functor, like the.
But anything practical that we would actually use in the course of normal programming? Because if I collapse all my types into a single type, it's kind of not usable. Sure.
Yeah. It's maybe not practically useful, but like it can be useful for defining other things.
Okay.
But yeah.
Thank you.
Yeah, so, oh my. Yay, okay. So yeah, I thought I wanted to give you some examples of these functors. The main one I want to get across is basically this idea of a directed graph, so or directed network. So I've spoken about that a lot. And I want to show you something really cool that you can do with functors. I'm a bit biased, I guess, but I kind of feel like if you look at things in category theory the right way, you can understand like what, say, graph theory, like the subject of graph theory is about. Almost, it sounds a bit too, but it's almost like you can write one tiny little expression and it basically corresponds to all of graph theory. It's pretty crazy. And I want to kind of show you how that works. But I think there's maybe a better example to start with to really try and convey this idea of a functor. So have a look at this. I'm going to make a category that has 3 objects. Like this. So these are just utterances in English. So I have 3 objects. One of them is called a man, one of them is called a head, and one of them is called a number. And I want to actually make a category. So I've got these 3 objects, and then we want to have some arrows. So we'll have identity arrows. I won't draw those. I'll draw some other arrows. This one here I'm going to call has. And this one here I'm going to call has as volume. Once again, these are just utterances in English. I'm not trying to tell you that they mean anything in particular. But you can see that they kind of maybe mean something to you, right? Like, oh, I should also tell you how composition works. So what happens if we compose this arrow here with this arrow here? Well, we get another arrow. Of course, it has to go like that. And the way I'm going to find an English phrase to associate with this arrow is I'm just going to add the word which in the middle. So maybe I should make that lowercase as well. So I want this to sort of commute, or this to be the definition. So what am I doing here? Well, this is an idea that David Spivak came up with a few years ago. It's called an ontology. It's a good way of doing knowledge representation using category theory. The idea is that you can make a category. It has objects as these indefinite noun phrases, and arrows which are sort of telling you aspects of these things, like functional aspects of these things. Like, so it's supposed to convey some kind of abstract notion, some kind of abstract knowledge. But you can read this and maybe it makes sense to you, right? Like if I say a man has a head, yeah, that makes sense, right? And it's also sort of defining like a functional relationship. If you think of whether I've written a man, think actually about the set of men or a set of men. Well, you can have like a function that sends every man to a head. And you can have a function which sends every head to a number, which is like the volume that head has. I don't know what volume a head has. Yeah, I don't know. But some number, I guess it depends what units you're working in. But I've just told you about a load of objects and arrows. I haven't told you anything about sets and functions. So, what about if we actually want to instantiate this? Like imagine that you want to make like a spreadsheet, maybe for all the people in your company, right? You want to record which head they have and which volume that head has. I'm not quite sure why you'd want to do this, but so what we can do, if we call this category C, then what we can do is we can consider a functor, F, from this category C to this category of sets and functions. Now, what's this going to do? Remember, a functor sends objects to objects and arrows to arrows. So let's think about this. What would it mean to have a functor like this? Well, what do we have to do? We've got this, our source category is very small. We've drawn it here. Our target category is huge. It's this category of sets and functions. So one of the objects here is going to be this set of these two guys. And another one of these sets here is going to be this set of heads. And so when we define this functor here, we're going to have to send this object here, which is called a man, that's going to have to get sent to some set. Yeah, that's part of what it means to define a functor. And this function here is also going to have to get sent. Sorry, this arrow here in the source category has to get sent somewhere by our functor. So it has to get sent to a function. Is this starting to become clear? So that would be the image of has under this functor. And so defining let me finish the job. So a number here, so this would be f of a man. This would be f of a head. That's the image of the object called a head under the functor. And then we're going to have this, which is going to be a load of numbers. And the image of has as volume is like that. So you can see that what we're really doing here, if we just define this category C, we're defining a sort of abstract schema or a kind of shape for our information. Or if you like, we're defining the sort of template for making structured sets. But if we actually want to instantiate this, we actually want to have a functor which goes from the category C to this category set. And this is really giving semantics to this kind of syntactic structure. So this is a recurring theme in category theory, is that you will often, if you want to speak about some kind of syntactical structure, you'll often start with some kind of small category or something where you can talk about the shape of your data, but there aren't really any extra equations and the stuff there doesn't really mean much. And then to make it mean something, you functor it into some place where your arrows actually mean something. Like with set, your arrows actually mean functions. So that's like the process of actually filling in your spreadsheet and writing down, okay, which men are we talking about here? Which heads are we talking about here? Which man is getting sent to which head? Defining that is like defining your functor. Okay, right. Okay, so what I want to convey now is basically what I was saying earlier. I was making this claim that with this idea of functors and with another idea called natural transformations, which I'll come to later, but that once you've got the idea of natural transformations, that's like your kind of Holy Trinity of category theory. You've got your categories, you've got your functors, which are maps between categories, and you've got your natural transformations. I'll get to those later, but basically, natural transformations are almost like maps between functors. And once you've got these three, you can start to assimilate most of the definitions in category theory, because these are the central ideas. And what I want to try and get across is that with this kind of information, like, for example, you can get a handle on what a graph is, or a directed network, like, in a very nice way, in a way which, yeah, it's pretty cool. So I want you to have a look at this graph G here that I've drawn here. So when you look at this, just forget about all the category theory for a second. This is nothing to do with category theory. This is just a directed network, okay? So it has vertices, A, B, and C, and then it has these edges, 1, 2, and 3. And what I want to show you is that actually we can describe this graph, or any graph, using the idea of functors. Okay, so I want to try and convince you that actually every graph corresponds with a functor. So I want to try and make it so that when you think about graphs, you're going to think about functors. The reason is because, well, it's so much neater, because it turns out that what I'm going to say, it doesn't just work for graphs, it works for a whole plethora of structured sets. So there's all sorts of things in mathematics that you'll encounter where you'll have like a load of sets and a load of functions. And if you have all of that info together, that's like one example of a mathematical object. And the method I'm going to show you works more generally. So it's good to know. So yeah, our problem then is to take this information that's in this G here, and what we're going to do is we're going to encode it in terms of sets and functions. Now, it's probably something that you folks like with the functional programming. You know, how are we going to encode it? So what we can do is we can say, firstly, what's the set of edges that we have, and what's the set of vertices that we have? That's like a good first thing to do in encoding this blue structure G. So let's have a look at the set of vertices. We see, okay, the vertices are A, B, and C. So we'll have this set of vertices here, A, B, and C. Okay, we've got the vertices. We also want the set of edges. So the set of edges, 1, 2, and 3, they are here. But we're not done yet. Of course, it's not enough just to know what the set of vertices and edges are. We need to know how these things are connected up. So we need to, the way we're going to think about this is that we want to know what the source is and what the target is of every edge. If we know that, then we know everything about the graph. We have all the vertices, all the edges, and we know what the source and the target is for every edge. So the way we're going to encode that latter information is with a couple of functions. So we're going to have a function called S. That's going to tell us what the source vertex is of every edge. And we're also going to have a function called T, and that's going to tell us what the target vertex is of every edge. So hopefully you can see that this information here is equivalent to the information on the left. Is that the case? I'm seeing some nods. Yeah? Okay. Now, what kind of information are we really having on the right here? Right, try and think about it from a kind of category theory point of view. Try and think about it from the point of view of objects and arrows. What kind of information are you really telling someone when you're telling someone what a directed network is? I would say that it looks something like this. Maybe I think I'll copy this to the bottom so I've got more space. Yeah, I would say we've got something like this. We have our category of sets and functions, and then we're going to have an object here. That's going to be our set of edges. And we're going to have an object here. That's going to be our set of vertices. And then we're going to have a source function and a target function. Do you see that? Like, to define what a graph is, we just have to, if I can tell you what a graph is, as long as I give you two sets, and then I give you these two kind of parallel arrows or parallel functions, things that are telling you how to get the source and the target. So, what a graph really is, so I'm going to define this category now. You remember before, I cooked up this kind of abstract category C, and it was like a shape of information. I'm going to do something like that again. So I'm going to make this category here, and it just has two objects, and it just has, okay, I'll color them because it's nicer. It just has two arrows like this. Now, what else? Well, it's going to have identity arrows. I'm not going to draw those. And we have to say how arrow composition works. But if you think about it, you can't really do very much interesting arrow composition in this category anyway. So I don't really have to tell you very much. Like, in a way, that picture is enough to show you what I'm talking about. Now, what about if I consider a functor, G, from this category into set? What's that mean? What does a functor have to do? It has to send objects to objects and arrows to arrows. So let's think this through. What's this going to do? Well, I'm going to give these some names. It might contradict a bit the naming convention I was using earlier, but I think it's still a good idea. So I'm going to call this object E. I'm going to call this object V. I'm going to call this S. And I'm going to call this T. So what are we doing here? Well, I want to define a functor from here into set. So what's set? objects as sets, arrows as functions. I have an object here. I've got to send it to an object of set. So what set shall I send it to? Well, how about if I send it to this set here? I better do this right. 1, 2, and 3. Okay? So that's the set that I want to send this object to with my functor. Okay, so I could call this G of E. Why am I calling it G of E? Because it's the image of the object G under the functor. Sorry, it's the image of the object E under the functor G. Okay, and it's a set. What else do I have to do? Here's another object. I have to send this to a set. So I'm going to send it to A, B, and C. That's G of V. Now here is an arrow of P. I have to send this to an arrow in set. So I'm going to send it to this. Has to get sent to a function, right? That's going to be G of S. And I'll send T to, I'm basically trying to make this picture, okay? So finally, I have this arrow T here. I have to see, that's an arrow in this category P. I have to send it to an arrow of set. I have to send T to a function. Which function am I going to send it to? I'm going to send it to the function that defines how my graph should be connected up. So I'm going to send T to this. Well, this one I've already drawn up here. So how does it work? I think it works like that. So that's going to be G of T. So can you see that a graph is exactly the same thing as a functor from this category here into set? Right. Like, so basically now you can think of a graph, it's just like a certain kind of structured set, and it really, like, this tells you the structure. So you could come up with a more general definition now, right? What if you came up with a definition of like a higher dimensional graph, where you have like a higher dimensional edge that goes, then you could just change this template a little bit, right? You could sort of extend it. So you could say, okay, let's say that there's another thing here called I don't know, I'm not very good at hypergraphs, but let's call it a hyperedge or something. And then we have like extra arrows down here. And then when we functor it, that's going to give us a more complicated, a functor from such a more complicated schema is going to correspond to a more complex kind of structured set. Yeah?
So in the set category, I think this is correct, right? The set category, the top one that you...
Yep.
Okay. Are the left and right, are those... Is the left one object and the right is one object? Or is the 1, 2, and 3 individual objects?
Yeah.
You're drawing individual arrows.
The whole thing in the bubble is an object, because the objects in set are sets. And when I draw like a big blue bubble with 1, 2, and 3 in it, that's like supposed to indicate the set with elements 1, 2, and 3.
So how should I understand the individual arrows between...
Right, that's a good question. I wish I didn't have to draw them, because they're not supposed to be arrows. They're supposed to be indicators of how the functions are working. So to draw this properly in category theory, it would look more like this. It would, we'd just say...
Is it in reality just one arrow and you're showing which elements map?
Yeah, and that's a brilliant question, because I think that was confusing. Yeah, so this is the way it would really look. So really, we've just got this object here of set. And yeah, it has elements inside that I've depicted here, but I'm kind of breaking my own rules by doing that in a way. But really, we just have that this is sent to this object, this is sent to this object, this is sent to this arrow, this is sent to this arrow, but really this arrow is a function, and we're kind of drawing it in expanded out fashion up here. And these aren't really arrows in the sense of category theory, they're just saying which elements get mapped to which elements. Yeah, great question. Do you want to?
So it's like the whole color green is one arrow in a way, or everything that is with green is one arrow.
Yeah, yeah, that's it. Yeah, like it's, I don't know, it's a bit of a, not the easiest thing to draw. It's one of those things that it's easier to do on YouTube, I guess, but yeah.
Sorry, just one more question. So the set here, and also in the example before with the man and the head, is this the set? Is this a category of just these objects that are depicted here, or is it the set of what? All the objects?
All of them. I'm just
everything that exists?
Yeah, yeah. So we're functoring into this category which has all sets and all functions, but we're only hitting a few, right? Because we are functoring from this category here, which only has a couple of objects. So when we look at the images of those, we only really have to think about a couple of sets at most. But there's loads and loads of other stuff that we're not drawing.
But it could be also, if you look only at these two elements, it's a category, right?
That's true as well. Yeah, that's true as well. But yeah.
Thank you.
Was there a question way back?
Yeah, so we just understood that, well, there is a kind of direct correspondence between DAGs, I mean graphs, and, well, categories of any form.
Yeah, there's this correspondence between the DAGs, or the directed graph. Oh, sorry, no, just directed graphs. Don't have to be acyclic. But yeah, there's a correspondence, a one-to-one correspondence between the directed graphs and the functors intersect.
So if you have a category P of where objects are edges and vertices, and there is if you have a functor G, then you can basically represent any graph with this functor G. My question is like, okay, that's maybe just another way to represent a graph. There are many notations. What does this knowledge really buys you?
Yeah, at this point it doesn't look that much, but the same idea can be used to describe lots of other structured sets. So another example, should I do it now? Yeah, I think I'll do it now because I think it might help to answer your question.
I'd like to clarify this a little. So like after applying G, so we have basically two functions, and the arrow, first like green and red arrows will correspond like the inputs and outputs of these functions from edges to vertices, like which edge points to which vertex and vice versa. So the knowledge kind of tells us that there should be two functions, and having them implemented will give you a notion what this graph looks like.
Yeah.
That's just so you can represent this graph with those two functions. And you can compose graphs by composing those functions and whatever. But that's just, again, another way to represent graphs with a couple of functions.
Yeah.
You can represent them with cardinality matrix and some other way.
Absolutely. So to answer your question about what it buys you, I'd say it buys you two things. One of them, which we'll see in a moment, is that, and I think this is the best bit, is that we're going to get a notion of maps between graphs almost for free. So if you define what a graph is, you tell me one of the definitions of a graph, I could ask you, what would be a good notion of maps between those graphs? And we're going to get a notion like that for free out of this framework.
By composing the arrows in the source category before applying the functor?
No, it works a bit differently. So it's more akin to the idea of a functor that I was explaining before. It's like, how do we send one graph into... So for example, like a subgraph. You know, if you have a subgraph, that means there's like sort of like an inclusion function from the first graph to the second graph. That's like a map between graphs. There are other maps between graphs that fold edges on top of each other. But what is a good definition for a map between graphs? Well, maybe you can come up with a good definition, but you'll see that idea fall out of this framework for free once we get to natural transformations. But the other thing that you get out of this is that it applies to not only graphs, but any kind of structured sets. So we're going to see later other kinds of things which are interesting, like a discrete dynamical system, or a simplicial set, or a hypergraph, or even a function. Each of these also has exactly the same kind of form, in the sense that we can define some little category like P, and then we can say, what's a functor from P into set? And it corresponds to a structured set of that flavor. So that's like the real big payoff,
it's kind
I
of
guess.
The knowledge that the operations under the object are composed the same way in all of the categories, basically.
Yeah.
Does associativity of function composition in one category, when you use a functor to map it to another category, does it imply associativity of function composition in the second category?
Oh, that's a question. Off the top of my head, well, I mean, if you're functoring into a category, then you have to have associativity there anyway. So it's like, if you're going to play the categories and functors game, then arrow composition is always associative. But I think you could imply that it has to hold on the image by the fact that functor application preserves composition.
So I did actually mean commutativity. I mean commutativity of two different arrow paths, essentially.
That's what I meant to say. That's a great question. Yeah, that's true. If you have a commuting diagram in your source, then in your source category, then the image of that has to be a commuting diagram in the target. And you can use that to define some interesting structured sets, right? So maybe you don't just have a load of sets and functions, you also have some equations that you want to be true.
And how is that guaranteed? By one of the laws that you talked about?
by the law that if you have two arrows in your source category and you compose them and then you map, you get the same answer as if you map first and then you compose later. That means it basically is the same thing as preserving commuting diagrams.
Okay.
Yeah, so to give another example of one of these nice structured sets, this is actually a really cool example that it's going to show you another side to category theory, maybe. So we're going to cook up a category that tells us how to do arithmetic. Okay, this is cool. So we're just going to have one object that we're going to call dot, and we're going to have an arrow called 0, and an arrow called 1, and an arrow called 2, and an arrow called 3. I mean, we go on forever. And what do you think we get if we compose the arrow 1 with the arrow 2? If I tell you this has something to do with addition. Anyone? Yeah. So arrow composition works just like arithmetic. So we have this category. It's like a monoid or something, and it's telling us what plus what equals what. Now, what happens? So I could actually, maybe I won't do it like that. What shall I call this? I'll call it L for loopy. So we're going to consider a functor f from L into set. You know what? I'm going to take a 10-minute break, and maybe you can think about what this is. What does this correspond to? What kind of data structure do you think this corresponds to? All right, so I'll come back at 4.
It'll be a 5-minute break.
A 5-minute break, yeah. I'll just go and have a look at the outside. Good. All right. All right, well, thank you for your patience, you resilient learners. We're almost there. I think it's like 1 3-hour block to learn category theory is kind of a lot. Like I would recommend bite-sized chunks. Maybe check out my Category Theory for Beginners YouTube channel. I actually have some 8-hour videos on there, so maybe you can watch those in bits. But yeah, did anyone get to the bottom of this conundrum? Yeah?
I mean, I was thinking about something, but I thought that the dot has to be a set. So I would say that would be the set of natural numbers, maybe.
Could be.
Could be. And I was thinking maybe the arrows can't be the same. They have to be somewhat indicating what the number is. So I was thinking maybe union 0 for 0, union 1 for 1. But I don't think that really works out. But I thought it's somewhat in the way of that.
I think you can do something like that. So let's think this through. So firstly, this is a little bit of a weird way to write what this category is, in the sense that it's almost like overkill. Firstly, 0 has to be the identity if composition means adding, right? Because adding 0 to anything just gives that thing back. Secondly, 2 here, okay, we normally say 2 is 1 plus 1. I would say 2 is 1 after 1. Oh, good, yeah. I thought I'd see confusion, but yeah. So if we compose the 1 arrow with the 1 arrow, we get the 2 arrow. And similarly, 3 here is 1 after 1 after 1. And so because of the way that functors work, it turns out that we only have to think about what happens to this arrow. So we know that this is going to get sent to a set, and we know that this is going to get sent to a function from that set to itself. After we've fixed that, the way everything else works is forced. And so what we end up doing is we're going to send this this dot here, that's going to get sent to a set, let's say S. S is f of dot. And then this 1 here is going to get sent to a function. Like that. That's going to be the image of the arrow 1. And so this is the sort of data structure that we end up with. It's a set together with a function from that set to itself. And what I would call such a thing is a discrete dynamical system. Okay, so for example, I could set S to be this set. Let's say it's a set of 3 elements, A, B, and C. And then I have this sort of, I could call this my update function. And so my update function might send A to B, and B to C, and C to itself. So for every state of my dynamical system, I have to tell you a sort of successor state. And that's what this update function is doing. And so I claim that a discrete dynamical system is the same thing as a functor from this thing here into set. And so we see down another family of structured sets. We've seen the graphs. A graph is like 2 sets, and these 2 functions that tell you how things are connected up. That's one kind of structured set. That's like a functor from P into set. So that's like the sort of template for that. And now we have another example. This is another kind of structured set. It's called a discrete dynamical system. And it's now just one set, which we could think of as a set of states, together with an update function. So, and you can imagine, in fact, I would encourage you to, like, it's a really great exercise, maybe one of the best exercises you could do, is to sort of try and write down the first few categories you can think of. Like, say, try and write down all the categories that have, let's say, 3 or less objects and 5 or less arrows. And then think about for each of them, what's it mean to have a functor from that interset? And what you're going to discover is that there's all sorts of structured sets which you can talk about using that. But we want to do category theory. And so we're always asking, what are the arrows? Right? Whenever someone tells you about a mathematical object, you've got to ask them, what are the maps between these things? So if we have two graphs, what's a map between them? Or if we have two dynamical systems, what's a map between them? And to get at that, we need our final concept, which is the idea of natural transformations. So this is the home run. I'm just going to go over this very briefly because it's a lot in one sitting. So here's the definition then. So let's say we pick two categories, okay? And then we can, like C and D. And then we can think of functors from C to D. So maybe a case you're interested in, maybe I got you interested in it, is this case where C is equal to this category P. Remember the one with the two parallel arrows? And D is equal to this category set. Okay, so maybe that's a case that you can have in your mind, right? And what I'm telling you is that, yes, you can think of all these functors from P to set. Yes, they correspond to graphs, and we have a set of them. Sure, there's a set of graphs. It's better than that. We have a category of graphs. So we're not just getting this idea of these graphs, we're going to get an idea of arrows between them. So these graphs, or equivalently these functors, they're going to become objects, and we're going to have some arrows between them. Basically, I want to tell you what is the right idea of a map between structured sets. And this is our final thing to understand. It's called a natural transformation. So I'll tell you what a natural transformation is in general, but intuitively, very kind of hand-wavy way of thinking about it is like this. We have our category set, and it's going to have objects corresponding to sets and arrows corresponding to functions. We also have this category of categories. It has objects corresponding to categories and arrows corresponding to functors. But there's something else in cat. There are arrows between parallel arrows, and they're called natural transformations. So this cat is even better than a category. It has even more structure. It doesn't just have objects and arrows. It has these things called natural transformations, which can sort of compare parallel arrows. Why do we care? Well, we care, for example, because let's say we pick P and we pick set. So then a functor G from P to set corresponds to a graph. And if we have another functor G dash, that corresponds to another graph. And then it turns out that this idea of a natural transformation gives us a good notion of maps between those graphs. So that's maybe why we care in the context of this discussion, although actually pretty much the whole of category theory is kind of hinging on this idea of natural transformations. In fact, I think when they discovered category theory, first they discovered natural transformations, and then they kind of worked backwards, and then they defined functors, and then they defined categories. So what is a natural transformation? This is the final definition we need to understand. So maybe I'm just going to sort of read this out loud a bit. Say in general, we have a category C and a category D. And we have these two functors, G and G dash. Now they both go from C to D. I say they're parallel, right? I always say that arrows that have the same source object as each other and the same target objects as each other, that's what I call parallel. So these are sort of parallel functors. That means we can have a natural transformation alpha from G to G dash. What does that mean? Well, I'm spelling it out here. What it means is that, so, like here's an object in our category C. When we apply the functor G on it, we get this object here, G of A. When we apply the functor G dash on it, we get this object here, G dash of A. The natural transformation consists of a family of arrows. We want an arrow like this, alpha A, which goes from G of A to G dash of A, and we want to have one of those for every object A in our source category. So what a natural transformation is it's a family of arrows in D. We've got one of those arrows for each of our objects of our source category. And so that's, and then we have a certain condition that this family of arrows has to satisfy. Basically, it has to sort of play well with the structure that we have, in the sense that for every arrow F in our source category, we have to have that this kind of square here has to commute. Okay? So that's the definition of a natural transformation. It's a little bit like, I wouldn't worry if you don't get the idea straight away. It takes a while to get used to it, but I'm claiming that this is really, well, it's a very natural idea, although it might not look it when you first see this. And so let's, yeah, you know what? I'm gonna wind up now, because I've sort of shown you the basic idea. I didn't quite get the time to get all the way to what I wanted to do. Basically, I started off earlier on by showing this picture of the king and making some kind of bold claims that you will know an idea by the company it keeps and so on. And maybe if I had another hour, I could, well, no, it's too much for someone who's just starting out with category theory. I think it's good to take this in bite-sized chunks. But basically, there's this thing called the Yoneda lemma, and what it allows you to do is you can look in these categories of structured sets, and you can identify just a few very special objects. And these objects are sort of like fundamental particles. Okay, I kind of think of this as analogous to physics. You know, in physics, if you have like your fundamental particles, and you know what happens when you fire those into your structures of interest, you can learn about other kinds of matter. And in a similar way, in each of these categories of structured sets, there's a way of finding these special structures. Like, for example, in the category of graphs, there's two very special graphs. A graph which just has one vertex and no edges. That's really special, because if you know about that, and you know about all the maps from that into some other graph, you know how many vertices that other graph has. So this gives you a way to understand the structure, or at least some of the structure of that other graph, just by knowing about the arrows that go into it. The other graph that's very special is a graph that just has a single edge between distinct vertices. So these are kind of like your fundamental particles in your category of graphs. And it turns out that if you have those, and you know the maps from those into your graph of interest, it's like knowing what's going on inside that graph. So it's this kind of idea of being able to understand what something is intrinsically versus sort of extrinsically. So like if you want to describe like a person, for example, you could describe them kind of internally, like, oh, their brain is wired up in such a way, their nervous system, a sort of internal perspective on what a person is. But you can also describe them externally, like where do they live, or who are they friends with, or whatever. And in some sense, in some special cases at least, this Yoneda lemma like tells you in a very precise way how these things are unified. And actually, when you get really into category theory, you start to see that almost all of the results in category theory end up boiling down to this Yoneda lemma. So it's quite a kind of very interesting thing. But yeah, I'm gonna stop there. I guess I'll end with some literature recommendations. So I got into this stuff through Bartosz Malowski's Category Theory for Programmers. He's got a course on YouTube, which is brilliant. Especially, you folks know Haskell, and he uses Haskell to explain all the examples. There's also a corresponding book. I have my Category Theory for Beginners course, which goes through all of these things in great detail. Apart from that, I think my top recommendation, if you're interested in it from a little bit more mathematical side, is this book called Conceptual Mathematics. I think it's accessible with like high school level maths, but it's an absolute masterpiece. It's written by William Levere, who was one of the best category theorists around, and it's very well written. So yeah, I'll end it there.
Yeah, thank you very much, Richard. Would you like to take a few questions, or is
yeah, a little bit. I've probably got to dash off in a while, but I've got time for a few. Yeah.
Cool. Yeah.
I was wondering, what's the relationship between say, the distributive laws in arithmetic, say multiplication distributing over addition, and the functor law, where the functor has to preserve composition?
Oh, that's a challenging one. I think if I was clever, I could probably come up with a better answer, but I don't know about relating it directly to functors. Like I say, there's probably a way to do it, but
I think at least the distributive law is an example of a functor, but maybe not.
Yeah, I think maybe it is. It could be. It could be an example. It could be an example. But definitely the distributive law from arithmetic, I thought you were going to ask something different about it. So, you know, what is it, like A times B plus C, and then you can expand out the bracket. So most people think about that as an equation relating numbers. But you can also think about, you know, your things as sets. And it's telling you that there's a sort of isomorphism going on there. So it's saying that, you know, okay, so this is something else that I didn't have much time to get into, which is these things to do with products and co-products. And it's probably something I should have mentioned, because you Haskell folks use these product types, right? And is it either? Is that the co-product?
Yeah, either is the co-product.
Yeah.
Tuples are product, yeah.
And so you know that there's a distributive law there as well, right? Like involving product and co-product. Like if you think about bags, if you think about sets instead of... Anyway, yeah, you can get at that as a...
Yes.
Yeah. And there's a pretty nice... there's in Levere, there's a very nice sort of theory of how that works. In a sense, understanding these things behind arithmetic, like the distributive law, it kind of... When you do a lot of category theory, you start to think that maybe those are really applying primarily in the category of sets. And then what happens when people are doing arithmetic is that they sort of forget about the sets and replace them with numbers, if that makes sense. But yeah.
Yeah, okay, thank you.
So you have functors to map between categories and natural transformations to map between functors. I have a sneaking suspicion that there are higher order transformations as well. And how far does that get you, and are they actually useful in practice?
Well, people take it all the way. So it's kind of like you know, this category of sets and functions is like this sort of quintessential example of a category, but it's like not something that you build yourself. It's like a natural kind of structure in mathematics, and that has just objects and arrows. And then cat, it has objects and arrows, and then these natural transformations between parallel arrows. And so cat is an example of something called a two category, or a two-dimensional category. So a two-dimensional category, it doesn't just have objects and arrows, it also has like arrows between parallel arrows. And then you can go further. So you can have a three-dimensional category that has, well, you could say objects, arrows, 2 cells and 3 cells, or 0 cells, 1 cells, 2 cells and 3 cells, and you can go all the way. And areas like homotopy type theory, they basically build on the idea of an infinite dimensional category. And that's not to everyone's taste, but it's an interesting idea, yeah.
Thanks.
Any other questions from anyone? Okay.
I often read about models of theories, but I don't know what that means. So would there be something like a model of a category theory? And what is a model of a theory?
So there's something called Levier theories, which are, I would say they're sort of an alternative to monads in some respect. They're like another way that you can kind of add side effects and pass this kind of landscape of things. In fact, you can sort of translate between monads and Levier theories to some degree. And a model of a Levier theory, it's basically a functor that goes into something like the category of sets. So I was showing before this idea that you can have a sort of schema or something like P, or like my thing with the heads and the men and things. So like a kind of shape of your structure, and then you functor that into set, and that ends up giving you this structured set. Now, if you have more structure in your source category, so you don't just have objects and arrows, you have a notion of like products of objects, make other objects, and you want your functor to preserve that. That's basically what a Levier theory is. And you can functor it into set. So for example, if you wanted to define what a monoid is, for example, maybe a monoid. Yeah, you can do that as one of these. It basically corresponds to a model of the Levier theory of monoids, which corresponds to a certain functor into set. But you can also, you can change set to be something else. This is something else very interesting that you can do. You can say, okay, maybe I don't want semantics involving sets and functions. Maybe I'd rather have semantics involving, say, vector spaces and linear maps, and then you'd be functoring into the category of vector spaces instead of the category of sets and functions. So you can interpret a model in different categories.
So is a model just coming up with the same kind of structure using different primitives or different concepts? What is meant?
To a degree.
Okay.
Yeah. I mean, I don't have time to unpack it properly, but yeah, it's ballpark, yeah.
Thank you.
Good. In that case, let's thank the speaker again. So the next thing on the schedule is the invited talk at 5, so in about half an hour. So see you then. Bye-bye.